Watch this. 9 out of 10 students, 90%, get binary and denary conversions wrong in exactly the same way. And the worst part? It quietly costs them their entire grade in the IGCSE exam. You think you know it, you write it down super fast, and boom, the marks are just gone. So we're going to expose this trap right now before you fall into it.
Okay, let's dive into this. See that glowing red wrong stamp right next to the calculation 11,11111 equals 256? Yeah, that right there is what I call the confident error. I mean, it looks right, right? It feels right, especially to a stressed student rushing through paper 1. But honestly, it is totally flawed. This single, tiny assumption cascades into a massive loss of marks on your paper.
So why on earth do 9 out of 10 students fail this exact conversion? Well, it's not because they don't get computers or because the math is somehow too hard. Nah, it's because under the intense pressure of the exam hall, they take a mental shortcut. You know the feeling? They try to guess the total weight in their head instead of methodically proving it on the page. And that shortcut? It quietly destroys their entire calculation. Let's expose the fatal flaw here. It's skipping the 128-column table. When you try to do this binary translation entirely in your head, or you just skip drawing the actual grid on your exam paper, it causes a complete cascade of calculation errors. You end up off by one single digit. And listen, in computer science, off by one doesn't mean close enough. It literally means 0 marks, nothing. So we are going to rewind right now. We're going to rebuild the correct foundation, step by step, so making this specific error becomes absolutely impossible for you.
Now, what's really interesting about this foundation is how beautifully simple it is once you actually visualize it properly. Just look at this 8-bit grid. Binary is a base 2 system. Basically, it's just a way of translating raw electrical states inside a CPU, literally just switches being on or off, into mathematical logic that we can actually read. Check out those columns. Each one represents a power of 2, starting from 2 to the power of 0 on the far right and doubling each time all the way over to 128 on the left. A 1 simply means the electrical switch is on, a 0 means it's completely off.
Okay, let's translate that complex hardware diagram into a simple, unbreakable habit that you're going to use in every single exam. Step 1, the very second you see a conversion question, draw your 8 columns. Just do it. Step 2, label them from right to left, starting at 1, then doubling to 2, 4, 8, 16, 32, 64, and finally 128. Step 3, take the binary 1s and 0s given in the question and map them right into those boxes. And step 4, simply add the on values together. If a column has a 1, add that heading's number. If it has a 0, just ignore it. It really is that straightforward, and doing this completely eliminates all the guesswork.
So, the crucial point we need to look at next is what happens when we try to add these binary numbers together, especially when we start pushing the computer's hardware to its absolute physical limits. Now, take a look at the binary addition section here. We're adding the denary number 200, which, as you can see, is 11001000, and the number 100, which is 011001000. Let's trace the math on this. Let's contrast what happens here. On the left side of our logic, an 8-bit system has a hard physical limit. The absolute maximum denary number you can represent with 8 bits is 255. That happens when every single switch is turned to 1. But 200 plus 100 equals 300. So when you actually do the binary addition step by step, carrying the 1s over to the left, it generates a 9th bit. This right here is called an overflow error. That extra 1 on the far left literally cannot fit into the 8-bit hardware architecture. It's kind of like trying to pour a whole gallon of water into a tiny pint glass. The extra data just spills over and gets dropped, leaving you with a completely incorrect result. Spotting this physical hardware limit, that is an easy, guaranteed mark in your exam.
All right, now I want to test your eagle eyes. We've looked at addition, but converting denary back to binary usually involves the subtraction method. Look right here at the Spot the Error challenge. We are converting the denary number 155 to binary, but there is a glaring flaw in the working out shown in those final steps on the right. Can you spot the mistake?
I'm going to give you exactly 10 seconds to mentally solve this challenge. Look super closely at those subtraction remainders. All right, 10 seconds on the clock, go. And time's up. Let's do the reveal. If you look at the sequence, after subtracting 128 and 16, we had 11 left over. The sequence shows 11 minus 8 leaves 3. But wait a second, where does that 3 actually go? The error was in failing to map the remainder perfectly. You have to drop that 3 into the 2 and 1 columns. 3 minus 2 leaves 1, and 1 minus 1 leaves exactly 0. If you miss putting the ones in those exact final slots, your entire byte is corrupted. Understanding this highly mechanical, step-by-step subtraction maps directly to the IGCSE mark scheme because, and this is key, examiners award marks for your working out in the table, even if you make a tiny little slip-up right at the very end. And this brilliantly illustrates why knowing the technical math is really only half the battle. Your exam strategy is just as absolutely crucial. The IGCSE examiners use very specific command words, and your precision with these words is what actually unlocks your marks. Look at the flow we have here. State means give a concise, sharp point. No waffle, just the facts. But a command word like evaluate, that requires an entirely different approach. You actually have to apply a technical judgment to a specific real-world scenario given in the prompt.
To guarantee full credit on those longer, high-value theory questions, you really need an architecture for your answer. I want you to memorize this high-mark answer template. First, give the precise definition. Second, explain the mechanism, the technical how or why. Third, anchor your explanation to a scenario example pulled straight out of the question. And finally, state the consequence or advantage. If you build your written answers using this exact sequence, you literally leave the examiner absolutely no choice but to give you maximum marks.
Real quick, before we completely wrap up our core foundations, I need to highlight a massive exam trap that catches students every single year. Consider this comparison, and please do not confuse validation with verification. Validation checks if data is sensible and allowable, like a range check making sure a month is between 1 and 12. Verification, on the other hand, checks if data matches the original source exactly, usually through something like double entry or a visual check. They are completely different mechanisms. If you mix up these definitions in a scenario question, you drop the marks instantly. No exceptions.
So, if you want to stop losing marks to completely avoidable traps like that one, and you want to finally understand the real mechanisms behind the computer science theory, then make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE. That way, you'll excel in your Cambridge examinations. We break everything down exactly like this in all our explainers, so you can walk into that exam hall with total, unshakable confidence.
Let me leave you with this one final thought. Now that you've totally mastered how your computer uses standard 8-bit binary to store positive numbers, think about the real world for a second. Real-world computers need to process negative temperatures, bank overdrafts, and sub-zero data too, right? So how does your processor use these exact same binary rules and columns to represent negative numbers without adding any new physical hardware? Well, it uses a brilliant logical trick called 2's complement, and we are going to crack that mechanism wide open in our next explainer. See you there!